thanks for the very nice introduction. I got into GIS 4 years ago through my wife. She said, oh, she works for ESI, and said, oh, that's something for you as an economist. And professors, and especially husbands, are sometimes very ignorant. So I said, well, I looked at it and said, well, it's a little bit too much effort to draw nice maps, and I almost stopped at that point. And then later on, I found out how powerful the analytical tools are, and I hope you will see how some of these tools could be used. So hereby, I publicly apologize to my wife for being ignorant. And the objective is to help prospective home buyers in the very early stage of their buying process. So it's nothing where you can predict house prices. So I have to apologize, nobody will get rich here by knowing where to buy and what to buy. But I think it will help home buyers a lot, because when I bought my first house, or our first house, then we were looking around in different areas. We had no clue what houses cost. We didn't know which areas were advantageous for us and which were not. So that is the objective here. The study area is currently Orange County. I would like to extend it to other areas. I'm looking forward to find collaborating partners, because it's a lot of work. One person can't extend it to too many areas. If you're interested, just let me know. My email is there. The project was funded by CoreLogic. They provided the data. California State University, already mentioned it, and the Haynes Foundation. And the project was developed between 2008 and 2012. The data behind the project are actually from 2009 to 2011, the house data itself. Normally, what one would do, you would say that's the theory, here are the data, and here's the application. And I would like to do it from the other side. I show you first the application, so you know where the journey is going to, and then I will show you how it was developed. So this is our house purchase plan. It's on the internet, so it runs in a browser. Has a little bit of introductory text here, a how-to section, a little video how to use it, and here's actually the application. And let's assume I'm looking for a house in Orange County. And I can look at it and see first, the average Orange County home has 3 bedrooms, 1,700 square feet, not pool, and it's not a foreclosure. And in an average location, it costs $435,000. That doesn't help me too much. I want actually a bigger house. I want 2,400 square feet. And you can see as I click here, you find at the right side the bill. Every extra square feet costs me more money. So when I add up to 2,400, the price would go up by $120,000 approximately. I also would like to get another bedroom. That adds $8,000. Not too much, but you have to think about it's not the bedrooms that make a house expensive, it's the square footage. The pool would be nice. Let's add the pool. And that adds only $8,000. You can't even buy a pool for that much money. But you have to think about, if you sell a house and has a pool, not everybody enjoys the pool. Some people would actually say, I'm willing to pay less if it has a pool. Some people would be indifferent, and some people would pay more. So on average, a pool adds $8,000. I'm also willing to buy a foreclosure home. And if I'm willing to go through that process, I can save an average another $47,000 approximately. Gets a bill up to $523,000. That still doesn't help me too much, because it's a price for this type of home in an average Orange County location. But I want to be in a very specific location that fits my needs and also fits my budget. And that's actually what the main purpose is. So I try to find the location here. And what happens is an application opens. Hopefully. Yep, there it is. On the left-hand side, we find summarized what we already saw, including the average home price. And then we have a map here. And I can zoom in. And I thought, well, here next to Dana Point, there's an area that looks nice, so maybe I would like to have my house here. And I can see for the area, the school quality is 917 API points, that's academic performance index points. The average is around 850 in Orange County, so it's a pretty good school. 5 minutes to the beach, I like that. 22 minutes to the park, to the next mall, well, a little bit far, I don't care too much. 0.3 miles to a park. Median household income is $150,000, and then when I look at the bill, $685,000, because the good school quality adds $18,000. The beach premium, because I'm so close to the beach, cost me another $66,000. Well, I can save $6,000 because the mall is far away. But the park I save way more than $6,000. The park premium is $10,000, and the premium for the household income is $72,000. And this is just too much for me. So I try another location. And what I'm doing here is, I heard Aliso Viejo is a nice area, so let's try that one. And still has a very good school quality, which cost me $13,000. It's 12 minutes to the beach, but now the beach premium that I have to pay for the house drops from $66,000 to $20,000, so that's okay. Well, it's a little bit closer, but I can still save something. Park premium I'm willing to pay. So now the overall premium is $70,000. I end up with $523,000. That is okay. Now I see, because all these little polygons, they are color-coded according to the extra price I have to pay for that location. And if I look carefully, I can see here is actually one that looks cheaper. So let's try this one here. And what I can see here, sorry, give this one. What I can see here, I save actually money. Where's the saving coming from? Well, the school quality is only 790. Well, if I don't have kids, why do I want to pay for the school quality? Why don't I move a little bit further away in a school attraction zone that has a worse school? Because I don't want to pay for it. So this house would be better suited to me. All the distances are pretty much the same, so are the premiums. So now I can go to my real estate agent and say, I want to have a house in the Aliso Viejo area, which is close to this school. And now I start my search process. That is way better than what is usually the way. Just go to an agent, and the agent would drive people around, and you would say, oh, this is not right, this is not right. Usually it takes weeks, not even months, before people really know what they want in which area. Also, the advantage is in terms of affordability. People don't buy something what they at the end can't afford. Because sometimes people just say, I don't care anymore, I want this. Well, here you know beforehand what you can afford and what not. So, how is this done? I will show that in 3 ways. I will show you how to generate the data, how to develop the model, and then finally how to publish the results on the internet. So one is database structure. Second, I mentioned it already, hedonic modeling. And the third is how to serve data on the internet. It sounds scary, but I can promise you I will not go so much into detail that I hopefully don't lose any fun. So where do I get the data? There are 3 groups of data I used for the project. The first ones are just transaction data. These were the data I got from CoreLogic, and they got it from the assessor's office. These are text data amended by some other data. So it has all the sales prices in that year, all the sold property in Orange County for the 3 years. It has the address, the number of bedroom, building square feet, date of the transaction, a pool dummy, it's a 1 if there is a pool, it's a 0 if there's not, and also a foreclosure dummy that shows was it a foreclosure sale or not. And foreclosure sale in that context means short sale slash foreclosure sale, because we know most of the sales are actually short sales and most of them don't go all the way to the foreclosure state. That is only a table. Well, if I want to do something with location, that's a problem. If I have just a table, I have to get my records, my actually sales records, somehow on the map. And the procedure is called geocoding. And what you can imagine about geocoding is there's like in the computer like a big address book. And for each of the address, the computer looks in the address book and finds the address. And then instead of having a telephone number, the address has the longitude and the latitude. And if I have the longitude and the latitude, I can put the address on the map. And after geocoding the data, here are my sales. 45,000 sales for the 3 years. These are not all the sales, because I filtered already those sales where the data seem not to make sense. I excluded houses more expensive than $2 million, because I believe with a computer without going on site, there's no way to figure out how much worse is a match. And I excluded houses less than $200,000 because they might have been more like apartments. So these were the restrictions that was left over. These are not only points on the map, because remember these records at the beginning, they had not only the address, they also had some properties, some attributes, sales date, square footage, and so on and so on. So if I click on one here, on this one, for example, which is somewhere in the Silverado Canyon in Orange County, you can, well, you probably not, you can guess, but I can tell you, it has the address here, it has the sale date here, it has the acres, it has the square footage, the year built, and so on and so on. So all the transaction data I need, they are already here and they are already on the map and I can process them. The second type of data are data that need to be assigned to these little dots. That would be something like income in the area. I might know what the area income is, but somehow I have to get the area income to each of these little sales records. There is where the GIS system comes in. And these are actually data for household income. And the polygons are census block groups. So for each of these polygons, I know what is the household income, the average household income, and some other information. What the GIS system does for me is I can overlay these polygons with the little dots, and you can think about the little dots drill into the polygon and suck out the information and add it to their own information. And you can see that here. Here, this little dot is in here, has all the information that it had before, but now it also has the average household income, in that case is $61,000, added to the record. So now all my records are amended by the household income. I can do the same thing for school quality. With school quality, I need a few GIS tricks, because what we would think, well, what we need is first we would think, oh, we need the school district. But it's not the school district that you send your kids to. Because what happens, you go to a good school district and end up with a bad school. You want to live close to the good school. And unfortunately, school attendance area information was not available. Now it's available as proprietary data, but it's very expensive, so I had to come up with something else. And I used the GIS system, and I think the best way to show you is I have as additional information here. I have other resources. We're just generating a few maps to give some extra information, and I have here school information. That takes a moment. That goes pretty fast. And what I did here, you see all these schools here. These little symbols, these little houses are all elementary schools. And for schools, data, available data, are incredibly good. The only thing what I needed was the academic performance index. But you can also get data about parents' education, about ethnic composition, and lots of other data. So what I did is, in a two-step process, I mapped first the schools, and let's zoom in a little bit and we can see it a little bit better. And then I created what is called season polygons. Each school is surrounded by a polygon. And the polygon makes sure that every point inside the polygon is closer to its own school than to any other school. You can see it here very well. See, the 9 is just in the middle. All the points here are closer to this school, while all the points here are closer to this school. So I use that as school attraction areas, which is not perfect, because the school could be a bigger school and could have a bigger area, and the school could be a smaller school and have only a smaller area, but for the estimation it was good enough. And here you see, for example, this school here, you get information, that's a very good one, 923 academic performance index. You can see the parents' education, yellow is college degree. Here we have some college. Here we have graduate degrees, and the red one is high school degree. So you get all this information, but this is actually only an additional information to the system. What is important at this point is to understand that each school has a polygon around it, where we assume that is everybody who lives in that polygon goes to that elementary school. And that's, of course, an advantage if it's a good school. So what I did then, after I have these polygons and I have assigned the school quality to the polygon, then I can do exactly what I did before. For each point, for each of my sales, they drill now into these polygons, get the school quality out, and add it to each of the 45,000 records. So now my records have school information too. They have average income information. The third group, these data don't even exist at the beginning. They need to be calculated. Because if I want to know how far is my house, or one of these, I have to know it for all of the houses, how far are these houses away from the beach? Then I could just measure the distance. That's not very precise. What I need is the driving distance, or even better, the driving time. And I have to calculate that for each of my houses. And the way I did it here, that's a little bit different map. This little white dots, these are all the sales in the 3 years with their location. And the triangles here are all the beaches in Orange County. And then I used the so-called closed facility procedure from ArcGIS, which basically says the beaches are my facilities, the houses are my starting points, they call them incidents. And then I find for each of the house, first, which is the closest facility. After I find the closest facility, I calculate the drive time. And then I add that information to the house. And in this map, you can see it's color-coded. All these houses here that are close to the red roads end up in this beach. These end up, nobody ends up in this beach, obviously. This one ends up in this beach, the orange one. Here, the dark yellow one ends up here, and the yellow ones end up here. So now I have for each of my houses, in addition to income and school quality, I also have drive time to the beach. I can do the same, and I did the same for drive time to major parks and for the shopping malls. I just put all the major shopping malls on the map and used a similar procedure. So as a result, I have a nice data set where all the information that I might need are in. Now I know the quality, school quality, income, number of bedrooms of the sale, the sales price, and so on and so on. So what I have to do next is I have to develop a model. And that's where the hedonic model comes in. And it's a hedonic regression model. And that can be actually explained pretty easily. And maybe just forget for a moment about the houses. You might say, oh, you buy a refrigerator and you pay for the refrigerator. Who wants to have a refrigerator? Nobody. Nobody wants to have an ugly refrigerator somewhere taking space. What you really want, you want something to freeze goods, and you want something to keep goods cold, and you might want something where you can get cold water. So you don't want the refrigerator itself per se. It's not you love the refrigerator. You love the amenities which come with the refrigerator. So now you might think, okay, so we don't look at the refrigerator price. The refrigerator is worth $1,200. No, what we want is we want to say, okay, a certain size of cooling is worth $400. Getting water, cold water out of it is worth $100. And being able to freeze is worth $500. So we put the amenities, we look at the amenities of the refrigerator rather than the refrigerator, and we assume we pay for the amenities and not for the refrigerator. That is very, very similar to a house. It's not the house that we want. We'll all say, I want this house, but it's not true. What we want are the amenities that come with the house. We want to have a nice place to live. We want to have the right to go to a good school or send our kids there. We might want to be close to a park so we can go biking. These are all amenities. We want to be close to the beach so we can lay in the sun. These are all the amenities. So instead of looking at the value of the house, in a hedonic model, we split the house in all its amenities, ideally. You never catch them all because you never have data for all. And then you try to find out which amenities provide how much value to the house. And we have all the data that represent our amenities. These little squares are supposed to be our 45,000 records. And for each record, we have school quality, that's a right to send our kids to a good school, the distance to the beach, and so on and so on. So what we have to do is we process the whole data in the hedonic model. We don't even have to look into it. We can just take it as a black box. And what the model spits out is a formula, which looks kind of scary. But it looks only scary because it has these ugly betas here. But when the model spits out the formula, it doesn't spit out the betas, it spits out numbers for the betas. So assume behind each of the beta is actually a number. Of the betas, what I can do is I plug in the square footage of a house, multiply it with the numbers. I plug in the rooms for the house, multiply it with the numbers, and so on, and I get an estimated price. That's one advantage, that's how I get the estimated price. But we also said we want to get the components that contribute to the price. Well, we have all these adding up components here. This is the square footage, this is what the component contributes for the square footage. Here is the component for the rooms. And I can calculate it because I know the data, the system spits it out. I know the number of rooms, I just have to multiply it and I know it. And so on and so on. And I have the miles to the park, I know the location where I want to put my house. I have a number, multiply that, then I know how much it costs me to be close to a park. So at this point, I could actually stop and could say, well, that's it. If I want to have an internet application, I just put the formula with the numbers on the internet and tell people, well, if you want to find out how much the value of a house is, just figure out how many square foot it has, then find out how far it's to the next mall, then find out how far it's to the next beach, and then take your calculator and punch in all these numbers, and then you get the result, which would be not exactly comfortable. It would be a lot of work and nobody would actually do it. But the results, that's why I say that, the results are actually already here calculated by the hedonic model. To see how it works, and that might be most interesting for students who actually use ArcGIS, we can, here it is. Oops, sorry. Here's ArcGIS, I opened it already. And what I run is a regression. First of all, I have all my data here. I can look, here's my table. Remember, we were adding carefully information after information after information to all our sales records. We were also adding a lot of things we don't need, so I deleted those already. And here are the data. You see here, there are points. Yes, there were points on the map. We have the address here. We have the longitude, latitude information here. And then, if we go further, we can see all the other information we will need. Time to the next big mall, distance to major parks, and so on and so on. So I have all these data. Only thing what I have to do is close this table here and run a regression. I actually run the regression in another software, SAS or SAS, which is very commonly used, but you can do it directly in ArcGIS. But unfortunately, I forgot what the command was. No problem. I remember it was called regression. Click hit. And we have two types of regression, two ways of regression. What I actually need is so-called ordinary least square regression. If I'm not sure, I can look at the help file. And I open it up. And then what I have to do is first I have to tell the tool where do you find the data. This were the data we just looked at. Then I have to say which is a dependent variable. That's the one I want to estimate. That would be the sale amount. And then I have here all the other variables. I just have to click what I actually want. So what I want is, I want as influence, as amenities, the square footage, the bedrooms, if it's foreclosure or not. This says not time to big mall, it says logarithm of time to big mall. I will tell you later what is the influence of the logarithm. For now, we just say good enough. It's basically the time it takes and then calculate the logarithm out of it. And here we have the distance to the parks. Here is the school quality, the income. And then I have a second variable where I haven't talked about it. It is a house price index. Because if house prices change, then I would have to do my whole analysis again. And well, hopefully house prices will recover. And if it goes up, then I would have to do it every half a year or every 3 months. But having this variable included, I can just punch in the new house price index, because it's part of the equation, and it will automatically be adjusted. So the only thing what I have to do every few months, I have to punch in a new number in my application, but I don't have to run the whole research up behind it again. That's what should be done maybe every 3 or 4 years. Then I click OK, and then it takes approximately 5 to 10 minutes until it's coming out, and I don't want to torture you. So I just close it, because I did it before, and I have the results here. And it gives me a lot of information here. There's an exclamation mark with a warning, and I will comment on that a little bit later. And here it has a very nice PDF file where it has all the results in there for me already. And this file is actually here, it shows me first the multiple r squared. I think it's good enough to say that's a quality measure of the regression. Best quality would be 100%. If you get that, something's wrong with your regression. You probably have an identity. Worst quality would be 1. 80% is a pretty good measure. Here we have the arrows, because we can calculate the arrow. We have the data. Our system calculates or estimates a house price index, but we know the correct price from the sales record, so we can estimate what is the arrow, and actually this system is not too bad. In average, the arrow is plus minus 40,000. That's not good enough for an appraisal, but it gives a pretty good idea how much a house is worth. And if you think about if you buy a house, $80,000, $40,000, that's pretty much where you negotiate about. So you can't expect the system to know how good you actually negotiate. The arrows are what's called normal distributed, same amount of underestimating than overestimating, gives a nice bell curve, so that looks okay. What is more interesting is, where are our betas? And the betas are here where it says coefficient. Here are all my variables, and I don't want to go on all the ones, I just interpreted very few ones. So let's look at the square footage. So the beta is 163, so that means this number here is 163. If I increase the square footage by 1, then this block will increase by $163, making the price $163 more expensive. Short version, increase square footage by 1, house price will increase by 163. And that's what I used when we calculated the premium. API, Academic Performance Index, $290 approximately. If school quality increases by 1 academic performance index points, breaks almost my tongue, then the price will go up by 287. You might say, well, so what? But if you think about it, the school quality in Orange County varies with almost 300 academic performance index points. So having a really, really bad school and having a top school is 300 academic performance index points. So let's be generous. This times 3 is 1,000. 2 zeros added, 10,000, 100,000. It can, in an extreme case, between the very best and the very worst, it can add $100,000. More likely it will add a few 10,000 or 20,000 just for living in a better area, in an area that has a better school quality. Can you imagine what that means for school policy? If you make your school better, all the houses in your area increase. The rate of return of making school better is actually incredible. It's unfortunately not collected by the same entity that makes the school better. That's a problem. That's why we would need taxes for, but nobody likes them. Last thing here, and I promised you I would comment on the logarithm. If you have a normal variable, we say if the variable increases by 1 unit, by how many units will the price increase? We did that 2 times. If we use logarithmic values, and we did that, instead of using our minutes, we just calculated the logarithm out of it. The consequence is that this one needs to be interpreted a little bit different. If the distance, the minutes to the beach, if they increase by approximately 1%, then the house price will decrease. So if I move 1% in terms of driving time away from the beach, then the house price will increase by approximately $500. You'd say, wait a moment, it's not $500, it's $49,000. Because it's percentage, I have to move the digital point a little bit to the left. So that means it costs a lot to live closer to the beach, and the effect gets stronger and stronger. And why did I use percentage instead of the absolute value? Because when we get further and further from the beach away, then the effect kind of wears off. If I live 1 hour, in order to get the same effect of 1%, or let's say I live, I live 100, let's not make it too difficult for me. So I live away 100 minutes from the beach, and now for 1 extra percent is 1 minute. But if I live 10 minutes from the beach, then 1% would be only 0.1 minute. So the effect wears off, and that makes sense. If I live far from the beach, or if I live very far from the beach, it's probably not a big difference. But if I live already close to the beach and want to move very close to the beach, that makes a big difference. Then for the distance variables, I used local values. So now we have everything. You know where the formula is coming from. You know how it is to interpret. You know how you get the overall price, and you know how to get the components that actually say that's what you have to pay extra for your house. Last thing is, how do we get that on the internet? And again, I have my results already here. So if I torture my users and say, well, figure out how far your house is away from the beach, punch everything into a calculator, I have everything what I need. It would be just extremely inconvenient. So to make it better, I use actually, in our times, we distribute things. I didn't forget to scare you with the word distributed server application. The application actually runs on 3 different servers. Each serves another part. One part runs at Pomona at our university. One part runs at ESRI here in Redlands. And one part, which is actually the web application itself, runs somewhere, I've never been there, Redmond, Washington, where the company is, where I paid for to run the application. And here's how it works. First thing the user does, the user fills out this little form. So now the computer knows how many square footage the user wants, how many bedrooms, and so on and so on. Since the computer knows all the betas, well, these are just numbers, the computer can calculate this part here. But for price estimate, we need the whole formula. But the user didn't say so far where he wants to have his house, in which location, so we have no clue how far it is away from the beach and so on and so on. What I did here, because we don't know at this point, we're plugging in here the average values. And then I calculated the housing price. So if this is the right values the user chooses, and I plug in here the average value, what's the house price? The house price is the house you chose in an average location of Orange County. And that was the result from the first screen. So now we have these polygons here. There's no nice map behind anymore, but these are like actually our school polygons. So for all of these school polygons, I know already the school quality. I added all the other information because I calculated for all these polygons from the middle actually, how far is it to the next beach, how far is it to the next mall, and so on and so on. So for each of these polygons, I have all this information. Well, if I have that information, I have the numbers, I can see how much school quality contributes to the price. I know the school quality for each of these little polygons. This is just a number. I know how much it contributes to the price. I know the distance to the beach for each of these numbers. I know that beta 7 is just a number. I know how much it contributes to the price. This is the information which is hidden here in this map. The only thing what I have to do is present it in a nice way and present it in a way that the user can click on one of these polygons, and these kind of ugly polygons up here are here again, they are just color-coded. Color-coded for the estimated price. That's what we have. The moment the user clicks on one of these polygons, the computer calculates for the polygon, or first shows the amenities, and then calculates for each of the amenity how much each of these amenities contribute to the price, and then spits it out here as the information and uses the complete form. And we're done. The user knows for the specific house he or she has chosen in terms of bedrooms and square footage, and the location he or she chooses, what are the amenities, and how much each of these amenities contribute to the price. Well, then the user would like it or not like it. The user doesn't like it, the user can use a different location without driving. If there's no way to find one, the user might go back and reduce the number of bedrooms. One comment here is the income was such a big, had such a big impact. So you might get the idea, who cares if I have rich neighbors or not? I just find a super nice location where I have all neighbors that have a little bit below average income. Then I save a lot of money and be very happy. Well, the problem is that's not going to happen. Because if it's nice, the neighbors have a lot of income. And also, it's not that you would think, are people crazy? They are willing to pay so much money just to be surrounded by rich people? That doesn't sound right, and it is not right. The interpretation is as follows. We didn't catch all the location influence here. Some is missing, we just don't have data. We don't know if the area is on a nice hill and has a beautiful view, or if it has any other amenities, or if the houses are particularly in good state, or anything else. What would happen? Well, if this is the case, the house price would be higher. Only people with higher income can afford it. So where are all these effects that are not considered measured? A lot of these effects are actually measured in the income. So high income stands not only for rich neighbors, it also stays for there are other effects that are not measured, and only because the house price is higher, it attracts people with more income, and so it just stands for the extra amenities we can't measure. That's why the income has such a high impact. Slide, I stayed well in time. I'm ready for your questions.